Hi class, in this lecture here we're going to move into section 3.3, and this is an application of the exponential function that we've been talking about in the previous section. So this is about uninhibited and limited growth models. Okay, so first thing we're going to do is just a quick check to make sure we're all on the same page. So I've got this function f of x, okay, so f of x is equal to 5 times e to the 4x, okay? It says then express the derivative. Okay, so let's find the derivative first, f prime of x. Well, you know, that's 5 is the constant, bring down the 4, e to the 4x, right? Just the chain rule here. So this is equal to 20 e to the 4x. All right, but write it in terms of f of x. Well, if you look here, right, let me just move the 4 in front here. So this is 4 times 5 e to the 4x. Okay, notice when I do that here that this is my original f of x. So my derivative here, f prime of x, is equal to 4 times the original function here. Okay, so what you're noticing here is that when you have a function that involves e, okay, and just e by itself, so like something like 5e to the 4x, not plus like 2x squared, something just with an e in it, okay? You can write the derivative in terms of the original function. So it looks like it's just a constant times the original function. All right, so here's a theorem for this. So a function y is equal to f of x satisfies this equation. dy over dx is equal to k times y. Okay, so here you're writing the derivative in terms of the original function y, or f prime of x is equal to k times f of x. If and only if your function is defined as in the previous example here. Okay, so notice here, c is some constant in front, and k is the value in front of the x and the exponent. And this holds for some constant c. And in this section here, what we're going to do is we're going to use functions of this type and talk about these uninhibited and limited growth. All right, so exponential growth is going to be what we're going to talk about in this section. All right, so let me give you the first example here. So find the general form of the function that satisfies this equation. dA over dt, so the derivative of a with respect to the t, is equal to 5a. All right, so notice here. Here's my 5, and here's my a. So if I look back here, dy dx is equal to k times y. Okay, so notice here, all I'm changing is instead of y, I'm writing a. So here's a. And then instead of x, it's t. So look here, for this expression here, because the a and a is the same here, k is equal to 5. We're seeing that right off the bat. Okay? So what this means then is a has to be of this form, ce to the kx. All right? In this case, it's in terms of y, a and t. So for in this case here, it's going to be a is equal to ce k to the t, because it's a t instead of an x. Well, we found out what k is. So here, this equation is ce to the 5t. All right, and that's what this is equal to here. So we want to expand on this now and talk about this as uninhibited population growth. So the equation dp dt, okay, so what p is going to represent is p is population, and t is some time variable, okay? So dp dt is equal to kp, or p prime of t is equal to k times p of t, is the basic model of uninhibited, so that's unrestrained population growth, where the population can be comprised of, so it doesn't have to just be number of people, so it's comprised of humans, bacteria in a culture, or dollars invested in with compound interest continuously. So it can be a bunch of different things. All right. In the absence of uninhibited or stimulation factors, okay, a population normally reproduces at a rate proportional to its size. Okay, and that is exactly what this dp dt is equal to k times p is. So the rate of change is equal to some constant okay, times the population size. That's exactly what's going on here. That's how it's reproducing. All right, so the only function that satisfies this differential equation is given by, what we had before. Okay, if P of t is equal to C E K of t, or in this case, P of t is equal to P sub 0 here, E K T. I know I had this down here, but P sub 0 here is the initial population. Like, think of it as your starting value. Okay, where t is time and k is the rate expressed in decimal notation. Okay, and just note at time 0 you're just equal to c, the initial value. Okay, so we're gonna have this be our population growth equation. Right, it's P sub 0, the initial population, times E raised to the KT. Okay, so T is some time and K is some rate. Okay, T is time and K is some rate. All right, and then P sub 0, as I said, is the initial population. Okay, the starting value. All right, let's do, so I just have a bunch of examples of this to help you, I know it might seem like a somewhat confusing topic, so to help it kind of make sense. Okay, so I'm going to do, instead of a population one, I'm going to do a dollar one first. So suppose the amount P sub 0 in dollars is invested in a saving account where interest is compounded continuously at this 7% per year. Okay, that is the balance P grows at a rate given by this. So dP dt is equal to 0.07 P. Okay, this is the rate of growth. Okay, so think about what's going on here, right? So if you look back here, this right here, this dy dx, they're giving you K. They're telling you the growth rate. Okay, so this right here, you can tell right off the bat that this is my K. Okay, so here's what we want to do. We want to find a function that satisfies the equation, right in terms of P sub 0 and 0.7. Okay, suppose that $100 invested, what is the balance after 1 year? And in what period of time will an investment of $100 double? So if you're getting 7% per year, how long will it take for you to double? Okay. All right, so let's go through this. So A. So find the equation that satisfies this. All right, so remember this is the P of t is equal to P sub 0, all right, times e to the kt. All right, well, what is your initial value, right? Like, how much money are you initially investing? It's $100, okay, your starting value. E, and then we told you what K was, 0.07 times T. So look at that, that's great. All right, you're just straight up following the equations, right? Going back right here. So B, how much will you have in the account? All right, suppose $100 invested, what is the balance after 1 year? So you're just going to take 1 and you're literally going to plug it in. So it's 100 times e to the 0.07 times 1. So if you were to plug this into your calculator, you would get roughly 100 times 1.072508. So you would have roughly $107.25. Which is great. It's a little bit more than 7%, right? Like, if you think about it, and that's because this is compounded continuously. And then C, the next question says, in what period of time will an investment of $100 double itself? Okay, so what that means is we want to find how much. Remember, this is how much you have. Okay, but it double itself, so $100 turns into 200. So I'm literally going to have to solve this equation here. So obviously divide both sides by 100. So you get 2 is equal to e to the 0.07t. You're going to take the natural log of both sides. So the natural log and the e will cancel out, so you get natural log of 2 is equal to 0.07t. So you're going to get t is equal to the natural log of 2 divided by 0.07. And if you plug that in your calculator, you're going to get roughly 9.9 years in this case. So it's going to take almost 10 years for that $100 to double itself if you're getting 7% compounded continuously. So what you can see here, here's another theorem. The exponential growth rate k and the doubling time t are related. Okay. So basically what you're going to get, and you can just see how I just solved in the previous example, the time it takes to double, okay? And this is with exponential growth rate. It's always just going to be t is equal to the natural log of 2 divided by k. And where k is the growth rate. Always. All right, let's try this one, just so you can see it in action here. Worldwide use of the internet is increasing at an exponential rate. Okay, so it's telling you that exponential rate with traffic doubling every 100 days. Okay, so it's doubling every 100 days. So what is, in this case here, the exponential growth rate? So if you look back here, you can actually solve, we wanted to solve for k here. So k is the growth rate. So k is equal to the natural log of 2 divided by t. In this case, it's the natural log of 2 divided by 100. And now if you take this and plug this in your calculator, you get 0.006931, which as a percentage, okay, changing this to a percentage, is 0.69%, and then it was in terms of days. Okay, so it's like 0.7% per day is the growth rate of the use of the internet here. All right, let's do another one here. So the world population has approximately 6.04 billion people at the beginning of the year 2000. Okay, and it's been estimated that the population is growing exponentially. Okay, so you got that exponential growth rate at a rate of 0.016 or 1.6% per year. Okay, so they're telling you the growth rate. Okay, dp dt is equal to 0.016p. So this right here, they're telling you the k. Okay. All right, t is time in years after 2000. Okay, so for example, when t is equal to 2, that would be the year 2002. Just so that's what this means here. All right, so let's find a function that satisfies the equation. Okay, and again, right here, assume that p sub 0 is, and so our function p is going to be defined in terms of billions of people. So when you get a number like 6, it's going to be like 6 billion people. So p sub 0 is 6.0400, and k here is the growth rate, 0.016. Let's estimate the world population at the beginning of 2000 when t is equal to 20. Or 2020, excuse me. So estimate the world population at the beginning of 2020. And after what period of time will the population be double that? Okay, in the year 2000. All right, so A here. P of t. Actually, let me write it all down here. P of t we know is equal to, when you have this exponential growth rate, it's p sub 0 e to the kt. Well, they're giving you p sub 0. at 6.0400. E, they're giving you K, 0.016 times T. I got it. So if I, estimate the world population in 2020. So this is, I'm just going to take 20 and plug it in. And if you grab a calculator, so I have an extra set of parentheses there, but if you have a calculator and plug this in, it'll be roughly 8.3179, and this is in terms of billion. And then, again, how long will it take to double itself, right? So we have just this equation. T is equal to the natural log of 2 divided by K. So this is the natural log of 2 divided by K, which is 0.016. If you plug this into your calculator just to save some time, you get 43.3 years, which is roughly the year 2043. So, it's going to come quicker than we think. Okay, I just want to end on talking about models of limited growth. Okay, so the logistic equation or logistic function, so P of t is equal to L divided by 1 plus B e to the minus kt, all right, and this is where k is greater than 0, okay, is one model for population growth in which there are factors preventing the population from exceeding some limiting value, okay? So what this means is you can't grow past this number, okay? Perhaps there's a limitation on food, living space, or other natural resources. Like it just, after you reach a certain amount of people, let's just say, you can't grow anymore. Like if you think about the planet Earth, right? Like we have limited resources, we can't support 100, 200 billion people, right? It just wouldn't make sense. Okay, so let's do this one example. This is a bacteria example. Spread by skin-to-skin contact or via shared towels or clothing, MRSA, I'm not going to try to say what it's actually called, but MRSA can easily spread as staph infection throughout a university, okay? So left unchecked, the number of cases of MRSA on a university campus T weeks after the first case occurs can be modeled by this equation here. So if you look here, okay, they're giving you the L, they're giving you the B, and then they're giving you the K. Okay, so you see L is 568.803. This B is 62.200, and K here is 0.092. And the reason you would have a limited growth model here, there's only so many people on campus, right? Like after you reach a total number of people on campus, like it can't grow anymore, right? Like the staph infection has run its course and it's gotten everybody on campus, or after a certain amount of point, people will start leaving campus. All right, so let's find the number of infected students 3 weeks, after 3 weeks, 40 weeks, and then 80 weeks. Let's find the rate at which the disease is spreading after 20 weeks, okay? And explain why an uninhibited growth model is inappropriate, but a logistic equation is appropriate for this situation. And then let's use a calculator to graph it. All right, so this one here, all you really have to do is just plug it into the equation you're giving. So A, so we want to find the people, and remember T is after T weeks. So you're literally just going to take 3 and plug it in. Okay, and you're going to get 11.8. So approximately 12 students are infected after 3 weeks. And then you can see after 40 weeks, plugging 40 into just this equation here, 40 in for T, you get 222. When you plug in 80, you get 547, and so on. So you can see it's growing, right? Like to go from here to here, whoop, big jump, and then another jump here. So it seems like it's growing whoop, really quickly, and then it's starting to slow down. All right, so the next question here, it says find the rate. Okay, so when they ask you to find the rate here, they're asking you to find the derivative. All right, the disease is spreading after 20 weeks. So they want you to find n prime of t and then just plug 20 in. That's what they're asking you for this one here. All right, so to find the derivative here, there's many ways you could do it, right? So you can rewrite this, just to go back, you can even rewrite this as and then just use the chain rule, or you can use the quotient rule here. It doesn't matter, you'll get the same answer. So I set it up using the quotient rule, and I'm not gonna break it down every step for you here, but I encourage you to follow along on your own here and watch, look at what this comes out to be and try it on your own and see if you can get the same thing. And so this is the growth rate here, the rate of change. Sorry, not growth rate, the rate of change. And when you take the value 20 and you plug it in there, you get the number 4.368. So what this means is after 20 weeks, the disease is spreading through the campus at a rate of 4 new cases per week, which is not a good thing. And then finally, look, unrestricted growth is inappropriate for modeling the situation because as more students become infected, first off, fewer students are left to be newly infected, and the logistic equation here displays the rapid spread of the disease initially, as well as the slower growth in later weeks when there's fewer students left to be newly infected. That's what's going on. And you can see here, if you were to plug this into your graphing calculator, this is what the equation looks like. So it looks like, some people are starting to get sick, and then whoa, there's a big breakout. And then after a while, it's going to slow down because there's not that many new people to get infected. All right, class, I hope this lecture provided you a quick introduction here to this uninhibited and limited growth models.